This problem is about finding the steady state conversion in MFR for the exothermic reaction. Okay, let us read the problem statement. A first order liquid phase reaction is carried out in a mixer flow reactor. The concentration of the reactant in the feed is 3 mol per meter cube. Volumetric flow rate of the feed is 60 into 10 power minus 6 meter cube per second. Density and specific heat of the reaction mixture are given. The volume of the reactor is 18 liter. The reactor operates adiabatically. Feed enters at 298 Kelvin. What are the steady state conversion and temperature in the product stream? Heat of reaction, no information about the temperature. We can take this to remain constant, and rate is given as K into C, of course C of the key component A. That way we will take it as it is. Units are given. The concentration of the reactant, and T is in Kelvin and E is in joule per mole. Where is E? Actually E is this quantity. So what is they are asking, this you should also use R in joule per mole Kelvin unit. That's a reason for giving this data. Now let us write the design equation. For that, the available data are written here. Concentration, volumetric flow rate, density, then what is it, specific heat, volume, every data is written here. And we know this rate expression. Then inlet temperature is 298 Kelvin. We are asked to find the exit temperature and the corresponding conversion. So here we are given with Ca0 data. Ca0 divided by rho will give us K mole per kg. Now what is the need for that? Because we are given with this specific heat in terms of what is it, kg unit, whereas we need joule per mole unit. Of course this is in joule per k mole unit, that is also fine. So how to cut, so before that, so we have this Ca0 by rho available. So what is the usage of that? See here, Cp is in joule per kg, so that we are converting that to joule per mole. For that we need to know the relation between kg and mole. So this is the available information. That is from Ca0 by rho we have k mole per kg. So this kg is now converted into mole. Actually this is 3 mole per kg. Yeah, right, fine. Now so Cp is converted into joule per mole unit, and delta H of reaction is available in joule per k mole unit. Convert that to mole unit. So 2.05 into 10 power 8 were the joule per k mole. So per mole it is divided by 10 power 3, so it will be having 2.09 into 10 power 5. So that's why we have this. So this is coming from this heat released per mole of A getting converted equal to heat needed to rise the feed from its inlet temperature to the final temperature of T. Okay. So now we have the expression of Xa as a function of T. Xa as a function of T, or this is a straight line relation. This is coming from the energy balance. Now we can write from mass balance, or what is called as the design equation of MFR. V by Fa0, tau by Ca0, Xa by minus Ra. Minus Ra is written in terms of conversion here. Now we know this tau information because volume data is available and volumetric flow rate is also given. So where is the volumetric flow rate? So this is the volumetric flow rate of the feed. So now we have this tau data available to us, which is coming to 300 seconds. So tau is written in terms of conversion. So using this thing, okay. Now we have tau as a function of or is xa as a function of tau is available. From material balance, xa as a function of t is available. Of course, that were a straight line, whereas here this is not a straight line. Always k is having exponential relation with temperature. So always xa versus t we can get from material balance as well, whereas xa versus t is available from energy balance. So what is needed is we have to find the temperature correspond and okay, always we have to solve this equation. To always to yeah, we can equate these two equations. No, which equation? This xa. Always we can substitute for xa from the energy balance, which is available as a function of temperature. So always this is written here, and the right hand side, which is tau k by 1 plus tau k. K you can write as a function of temperature, which is already available. So so otherwise this is the equation available. One is xa giving mass balance relation, another is xa giving energy balance relation. So they are connected by this single equation. Otherwise, so this in place of xa I have written from the equation of energy balance, and this tau k by 1 plus tau k is written. So now we have a expression of t, expression for t. Of course, we have to solve this equation to get the exit temperature. That is a objective. But is it solvable? Let us check it. See, we have, this is a linear thing, whereas here we have exponential contents, so we cannot easily solve this implicit equation. No, this equation is not explicit in t. You have to guess some value of t and keep on guessing it, so that left hand side and right hand side are getting balanced. So otherwise not so easy to solve. Instead, we can plot this expression of xa versus t and the expression of xa versus t from material balance. Otherwise we have two curves generated, one from xa versus t from material balance, of course, which is nothing but this thing. In what way it is t? Because tau is available and k is a function of t. So xa versus t is available from material balance. Okay, this is a k. So yes, which is giving a S-shaped graph. In what way? Because numerator and 1 by denominator is this peculiar shape. This kind of functions will have S-shaped graph. Of course, we can also verify that upon drawing. And yes, xa versus t from energy balance, that also we have, which is a simple straight line, nice equation. So there is in the plot of xa versus t, say ranging from 0 to 100% of xa. So we have this temperature for the temperature range, which is mentioned or not mentioned. Okay, we are guessing the temperature to be in that range. Of course, we are going to find the temperature. So starting from this temperature of which is given as we are 290 somewhere, 298 Kelvin. So in that we are working around the temperature around this 298 Kelvin. Otherwise 300 to 400 we can take. For that we can make a plot of what is it, t versus xa versus t from energy balance, which is a straight line, nice straight line. And the other one, which is material balance equation, which is xa versus tau and xa versus k. Otherwise xa versus small k. Small k is a function of temperature. So we have this S-shaped curve. So here now the intersection points, no, these points are the solution for these two equations. Otherwise, upon solving, we are heading these 3 points. That is the meeting point of this intersection point of material and energy balance gives the solutions. But out of which is a stable solution? Say, of course, this point B is an unstable one. for any changes in small any small changes in temperature. Say for any changes in temperature, material balance per this is the conversion corresponding from material balance, and that leads to generating what is it yeah generating heat, and by this much amount, and again it is going to heat it up because of increased temperature. So this point, if you try to operate from this point and slight positive temperature change will lead to reaching to this temperature, reaching to this operating point. Likewise, if there is any reduction in small temperature value, temperature by smaller amount, say for example we are having a reduction in temperature and we are reaching to this point. From this point, what will happen? The now this is the level. So this point, if you in comparison to this is the heat generation and heat removal. Heat removal is more. So what will happen? Yeah, better I will. There is a new separate discussion on why this is an unstable point. Okay, I will give a separate discussion why for this kind of S-shaped graph and a linear line passing through that thing, why this is not a stable point. No, that we'll see separately. This is a point, stable operating point. The corresponding temperature and the corresponding conversions are noted from this plot, and which is coming to be 445 degrees Celsius and conversion of 98%.